So I've already put out some autocatalytic clock reactions where the product causes the reaction to go faster and faster. So it just is at an increasing rate, and you can see that the reaction all of a sudden seems to finish. This one really is more of a true clock reaction. So you can see here in the reaction here that what happens is it becomes blue all of a sudden because the starch reacts with iodine. And that iodine is produced because the hydrogen peroxide is reacting with it here. But the problem is as soon as the I3 is formed, that reaction is quite slow. This one's quite fast. So whenever the I3 is formed, it's completely reverted back by the thiosulfate. And so that's the key, that this one's slow, this one's fast. And so this is the clock really here. So the amount of stuff of this you have, the thiosulfate. Once that runs out, then all of a sudden it goes blue. So it's a sudden. Okay, so that's called substrate-depletive clock reaction. In my mind, that's a true clock reaction. That's not good for several reasons, because it's the only one where you can't engineer it to do an initial rate to get the true rate of reaction, because you're just going to see when it's finished and that's it. And so you can only ever get the average rate. And so even though you've got the average rate, it is still a rate, all right? And so you can work out what the concentrations are and plot it still. And you'll see that with these two, the H plus is 0 water. Change the amount of acid doesn't actually affect the reaction at all. So it's not there, it's to the power of 0. The others are to the power of 1, so they're first order, and so they have just increase double, triple. It's not exponential, it's not second order, like to the power of 2 or 3 or more. Okay, so you can still do this and improve the experiment even though you're not doing initial rate, whereas all the others you can improve them to do initial rates. And so this is what solution A is made up of, all of this stuff, all of it basically, and the solution B is just this bit, all right? And so that starts off the reaction. This is just a quick demonstration. You can see it just within 1 second it changes, and we're just slightly decreasing it by 5% or something, and hopefully that's a constant rate. If you just kept on decreasing it by 5%, changing the volumes here to change the concentrations to get slightly different times. Not a proper rate, it's just divided by time. A proper rate has to be moles decimeters per second, moles per decimeter per second. You don't need to do that necessarily. If you're going to do it properly, you would. And that would be probably one of the most difficult ones to do, because not for average, but for initial it's almost impossible. How do I get those concentrations? Well, I grab these numbers here. You can pause it yourself and look at it, how I converted it to concentrations. Labeled formula substitute unit as always. And I've done the uncertainty propagation if you're doing a science report for this one here. Most importantly for this one, I've done the conversions and the calculations. There are separate videos for that. That's how I like it to be set out.